Okay, let's go into SolidWorks and look at some parts and, well, part models actually, and let's talk about some manufacturability aspects regarding the machining of these parts. So here we have an assembly. It's just a general assembly for training purposes. It doesn't really necessarily do anything mechanically speaking. Okay, looking at the plate from the top, as I said, it's 16 by 10. The thickness in this particular case is 3/8 of an inch. And remember that as you get more experience, you'll start referring to numbers, dimensions as fractions whenever it makes sense. Typically, this dimension here, you would not say it's 0.375 inches thick. That we really don't do that. Once you get used to it, everybody's got common language, common lingo. We just quickly say this plate is 3/8 of an inch thick. You have to cut material to size, but also you have to think about the flatness of the material and the thickness of the material. So just basic aluminum in this case is not necessarily flat enough for your application, especially something this big. Unless the manufacturer, the machining house, orders flat plates that have been ground to a specific flatness. And they often do that. Machining house, if they know, if your engineering drawing specifies that it has to be within a flatness of 5/1000ths of an inch. Go to a top view and we're going to zoom in on this area right here. So if you remember, that right there is a long cutout that in this case, let's see how thick is that. How deep is that cutout? Okay, 60/1000ths of an inch, 0.060. Okay, so that cutout there in blue is 60/1000ths of an inch. If we go back to the assembly drawing real quick so you can visualize why it's there. In this particular example, we have the cutout because into it we assemble this plate here. Okay, so real quick, let's open that up. It's a plate that looks like this, and it's going to be vertically assembled downward onto the plate. So basically that cutout is a pocket for this plate. Okay, going back to the plate, we're here. Now the question for you is, based on what we already learned about machining and what the limitations are, give you a moment to think about it. Why are these funky Mickey Mouse ears here on the left? Or why is this shape over here? Let me zoom in. We have that at the end of the right. Okay, the cutout that looks like that. On the other end, we have a cutout that looks like this, with the Mickey Mouse ears right there. Okay, so you should already understand that the reason for such geometry is the limitations of the manufacturing process. This assembly demonstrates different ways to assemble and join parts to each other. Okay, it's another phase of the course that you will be going through soon. Okay, but we have another plate here that is attached at the very end of this base plate, and it is flush. This face is flush to this face right there. Okay, so once again, we cannot have a sharp edge here at the intersection of these two faces. So we add an extra little round area for the tool to be able to get in there and generate the geometry that's needed for the pocket. But let's say we want to make sure that that this chamfer is machined. Okay, we want to make sure that it's machined. So let's make it, I don't know, 40/1000ths of an inch. Make it a little bit more noticeable. Okay, so as you can see now, it's more noticeable and it's at 45 degrees. If you provide an engineering drawing that calls out this chamfer 40/1000ths by 45 degrees, they're forced to machine it. They're not going to try to do this by hand. Same thing here. Let's have a closer look. Okay, since we're talking about chamfers, there's that same small chamfer here. Then it comes around the open-ended slot and it continues on the other edge. This would not be a final design. What is this? Okay, no, I don't want to rebuild. We would not leave this base plate as it is, as you see it here, because it's got this very sharp corner here that can easily hurt somebody. So we would implement further design details to make it a safe plate. Let's see. Let's talk about this one here. This is fairly simple. Also, as you can tell, very rough geometry. This is not designed for safety. It's got a bunch of dangerous corners and edges. Okay, so this is again just to talk about machining aspects. So as you can see, these are two possibilities of mounting a vertical plate onto a horizontal base plate and mounting them with threaded fasteners that come from above. Okay, in other modules, in other chapters, we'll talk about various ways to fasten parts, including from below or the side or any other such approach. Okay, but what we have here is mounting from above with threaded fasteners. So let's talk about the machining aspects. First thing we notice here, there are two different approaches to material removal of the parts. This plate here started as a rectangular block, okay? And obviously, let me zoom in a little bit. This and this right there is a rectangular cutout. That material had to be removed, in this case, through machining. And that happens on the other side as well, as you can see. Another alternative to doing such a thing would be what we have here, to remove this material here. Okay? So remember, we talk about how great things look on the computer when we're modeling. Just at a quick glance, looks great. It looks like the plates are going to mount properly. They're going to be secure. One of them is a little better than the other, but I won't get into that at this point as far as securing the plate to the base plate. But the computer makes it seem like, okay, there's no issue here. It's two holes on a plate, two threaded fasteners onto a base plate is going to work. Now, as an excellent engineer, an engineer with broad experience that thinks about all relevant aspects, you start to consider cost reduction or cost implications of your designs. Okay, to take a plate or actually a block, because this guy over here, this plate started as a big block and a lot of material was removed to arrive at this geometry here. So it's doable, but you need to think about the cost implications. It takes a long time to remove that much material, and also the volume of the material has a cost or a price associated with it. So basically you're removing a large amount of material that's just either going in the trash or it's going to be recycled. But it raises the cost of the part that you're designing. This approach here is a little bit better as far as how much material is removed, because we're only removing this and doing so from both ends. Okay, let's move on to another example. Let's talk about this here. Now we're designing a bracket for two stepper motors that are oriented at 90 degrees, as we can see here. The machining house, the fabricators, the manufacturers could have chosen to take a big block that is about, let's say, 3 by 3 and removed all the material that was necessary to arrive at this geometry. Another possibility is looking at this part, it very much looks like an angle, right? Well, let me say an angle meaning a structural piece, a structural extrusion that is called an angle. And let me show you what that is real quick. Let's say aluminum angle. And we'll look at some images. Let's see what comes up. Oh, there we go. So if you're familiar with structural components, there are two tubings of various geometries. There are either round tubing, square tubing. These happen to be called angles. Okay, so as you can see, that is the typical geometry of an angle piece. So the manufacturer could have taken, instead, they could have decided, okay, rather than taking a huge block, removing all this material and letting it go to the trash or recycling it, which is going to take a while and cost us more money. Well, potentially, okay? Potentially. We don't know for sure if it's more money or not. Let's instead cut a piece of angle and modify it to arrive at the geometry that the engineering drawing is calling for. Angles are produced usually by extrusion. The extrusion process is not very precise. So you don't have very good flatness on this side, for example, or here on the bottom, or any side for that matter. The flatness is not very accurate. It's not tight tolerance flatness. And also this vertical face compared to the bottom face of the angle, it's not necessarily very close to 90 degrees. So the issue here is that it may take longer to square up an angle in all sides so that everything is orthogonal, 90 degrees in relation to each other, and the flatness that you want is there. It may take longer to do that rather than, well, compared to squaring up a block. So those are the trade-offs. And maybe the answer depends on what machining expert you're asking. Somebody will have their own preference and maybe they'll claim that that's cheaper and faster. Somebody else may say the opposite is faster. But as professionals ourselves, we need to know enough to be able to produce high quality designs that are cost effective. Okay, now, what else can we say about this piece? So this particular design, you can see that has a fillet right there, or a radius, right? Let's close up on that. So if that fillet is critical to your application, then you're going to call it out and you're going to specify a tolerance for the radius. If you remember, we talked about each cutting tool has its own capability. One of them being how deep it can effectively cut. Let's see. Rounded edge end mill. Let's see what comes up here. Okay, these are actually the opposite. These are for an external edge. Like, as you know, that's for an external edge. We need the opposite for an internal edge. So let's have a look at this one. Well, the image didn't open by itself. Oh, I see why. I'm clicking on links having to do with sales, not images. 1 second. Okay. Here we go. Let me zoom in a little bit for you guys. Okay, you can see that this end mill here, it's laying down horizontally, but of course you would typically use it vertically, has a rounded edge, as we saw before. So what could be done then, the other approach to generate this radius here, is to orient the part this way. Now, let's see. Now we're not looking at it from the top. Let's say we're looking at it from the front. And you have your rounded edge end mill coming from above downward. And it's going downward, downward, removing material and making several passes as it removes material. And because it's a tool with a rounded edge, cutting edge, is going to cut that radius right there. But the same applies to holes, for example. Let's just go ahead and create a hole here. We're going to, let's say for some reason, this application needs a hole at this location, and the diameter of the hole needs to be a 1/16 of an inch, 0.0625. As I said, with practice you memorize what these mean. What a fraction corresponds to as far as numerical value. So 6 to 5 inches, or a 1/16 of an inch, or let me put it this way also. You can say a 1/16 of an inch. You can say 0.0625, which is not too common, or you can say 62.5 thousandths of an inch. So think about that one. 62.5, 6.25. Yeah, 62.5 thousandths of an inch is another way to say it. More on that later. But in any case, so let's say we need a hole that's a 1/16 in diameter, and this hole, for some reason, maybe it's a conduit for fluid or a conduit for wire, for routing wire. I don't know. Any such case. Let's say it needs to go all the way. Let's just make it through all. Okay, as you can see, that hole is now going through the entire part. Think about the tools. How is this going to be manufactured? Is it manufacturable at all through machining? Or do we have, would they have to use a different manufacturing process? Well, of course, there's drilling. You know that drilling is a very common machining operation. So they can drill it. Let's talk about drilling first. Drill bits also, as you know, have their own cutting depth. So they would have to choose a drill bit that's 1/16 of an inch in diameter that has the ability to cut over 2¼ inches. Okay? I think all of this is making sense to you. Now, take it a step further. If you're drilling, in this particular case, the resulting manufacturing tolerance of a drilling operation is probably, for this diameter, 2 to 3 thousandths of an inch. Okay, total. So that means that your hole could be a 1/16 of an inch plus minus 1 or 2 thousandths of an inch. If you're routing wire through there, that should be fine. If you're routing, maybe you're pumping liquid through there, it's probably fine as well. Let's say you need a tighter tolerance because some critical pin of precise diameter is going into that hole. Now it gets a little bit touchier. Let's say that the pin that needs to be inserted into here is of a tight tolerance. And let's say that the fit between the pin and the hole has to be very close tolerance. It can't be sloppy. It has to be very tight. Okay, now you're going to get into other issues. You got to start thinking about, well, I know they can drill the hole all the way through, but the resulting diameter tolerance is not suitable. It's too broad. So I need to specify a tighter diameter. And at the same time, because the hole is so deep, now I need to specify, potentially specify straightness of the hole, or the axis. The axis of the hole has to be specified to be within a certain straightness. Okay, there's different ways to specify it with GD&T, geometric dimensioning and tolerancing. But the point is, drilling may no longer be sufficient or adequate for this particular feature based on your engineering drawing and the requirements that you're imposing. If that's the case, but what they would probably consider first, as far as machining is, they would drill a smaller diameter hole and then ream it. Okay, and in our previous videos and conversation, you saw what a reamer looks like, and a reamer in machining is intended to clean up a hole. Okay, you have a pilot hole, you have an existing hole that most likely was drilled with a drill bit, and you take a reamer and you come and clean up the hole. You clean up its surface, you'll get a better surface finish, and also you'll get a tighter tolerance diameter. So now you got to consider, okay, are there reamers that are a 16th of an inch in diameter that can go as deeper than 2¼ inches? So that would be a question that you can look into yourself if you choose to, or you can go directly to the manufacturers. Just give them a call, write a quick email. Hey, listen, I got a 16th of an inch diameter hole. Its diameter tolerance has to be plus minus half a thousandth of an inch, which is 0.0005. And unfortunately, I can't get around it. The depth of this hole has to be 2¼ inches. Can you do that? Is that possible? And would that be how costly would that be? Always ask that as well, because if you only ask, is it possible? Can you make that happen? Chances are they'll say yes. They'll find a way. You don't know how much they're going to charge you for it. So along with finding out if they are capable of doing it, also ask how much in general, roughly how much would that cost. Okay. And they may come back and ask you, well, we don't have reamers that go that deep, but we do have reamers that go 1½ inch in depth. Would it be acceptable to go from one end 1½ inch deep and then flip the part over and do it from the other side? Would it be okay if the two precision holes meet throughout the entire part? Is that going to be an issue to your design? Okay, then it would be up to you to answer that, to figure out if that is acceptable for your given application. Let's take a close-up here. So this particular bracket has a the holes are for socket head cap screws. Okay, let's look at a top view here. And you probably remember what a socket head cap screw looks like. And that's what they look like. Okay, cylindrical head, and of course straight threaded body. So this particular case, there's a counter bore for the head of the socket head cap screw, and of course a through hole for the threaded portion of it. By the way, fabricators, manufacturers are very knowledgeable usually. Make sure that you locate a few trusted, experienced manufacturers that you can rely on and go to them for questions. Okay, a manufacturer could come to you and say, hey, you know what, we can make this part, not a problem. It's a little difficult, might be a little pricey. Would it be possible for you to design it in 2 parts? Okay, that's something, excuse me, for you to consider. You could have the vertical plate is one piece attached to a second piece, which is the horizontal plate. And you can attach it with threaded fasteners, perhaps it's welded together, etc. The point is, there's an infinite number of ways to produce things. So be very, very familiar with the typical options, and we're here at the Academy, we're helping you learn what those are. Okay, and well, let's wrap up this video. So we talked about different manufacturing implications, cost implications having to do with tools, and we talked about depth, capability of each cutting tool. We talked about stepping back and considering alternate approaches, maybe breaking a single piece into 2 pieces for the benefit of more cost-effective manufacturing. Okay, We talked about various other tools, and I hope you found this video helpful. Let's go ahead and move on. Thank you.